Dear students, welcome to the fourth session on galvanic cells. In this session, we will be dealing with the effect of electrolyte concentration on the electrode potential. Because we have already seen that one of the factors that affect the electrode potential is the electrolyte concentration. So, you can have the same metal with different electrolyte concentrations, you can have different potentials. So, let us think of one electrode, that is silver, which is dipped in a solution of silver ions, aqueous, concentration being 0.1 molar. Now, this electrode will give you a particular potential, because the concentration of silver ions I have taken as only 0.1 molar. Now, I am going to take another silver electrode itself with silver ions. Here the concentration is not 0.1, but I am going to take it as 0.01 molar. Here we have two electrolyte concentrations, one is 0.01, the other one is 0.001 molar. Now, see the potential of this electrode, both are silver and silver ions, but the potential difference. You can see why does it happen so, because in the first case you are having the strength of 0.1 molar, in the other case it is 0.01 molar. So, depending on that the potential varies, and a relation between the potential of the electrode as well as the electrolyte concentration is given by an equation known as Nernst equation. And this Nernst equation, you have it both for electrode potentials as well as cell potentials. Now, let us see how is it. We will consider first one of the easiest electrode, which is metal ion electrode. You are having a metal and metal ion electrode. Now, I am representing the equation, that is a general form where the metal ion has a valency of Mn plus. Now, here you can see that Mn plus aqueous takes up N electrons, giving M solid, and I have written it in the way that is reduction occurs at the electrode. For this electrode reaction, I can put the Nernst equation as E of electrode is equal to E 0 of electrode, E 0 or E naught of electrode. Here E 0 or E naught of electrode, as I have told earlier, it is the standard electrode potential. It is the standard electrode potential of that particular electrode, and remember this has been measured by connecting it with an SHE minus RT by NF. Ln stands for logarithm to the base e, or you can also call it as log. I am just saying it as ln, concentration of M divided by concentration of Mn plus. Now, I will define the terms, that is EL stands for the electrode potential, of which we are going to measure. E naught EL stands for the standard electrode potential. If I am taking silver, and this will be the standard electrode potential of the silver, which is predetermined. R stands for the universal gas constant, T is the temperature, N is number of electrons involved in the electrode reaction. You have seen that here in this reaction, this is an electrode reaction in which we have N electrons involved in that for the reduction of that metal ion. So, that is N, and F is capital F is known as Faraday which is equal to 96,500 coulombs. Okay. Now, you have written m in square bracket, which shows that it is a molar concentration of m. M means here in this case it is the metal. Then Mn plus, again that is also written in the square brackets, which shows that it is a molar concentration of the metal ion Mn plus. Okay. Now, since metal is in the pure form, okay, you can take the molar concentration to be 1 unity. So, the equation takes the form E of electrode is equal to E naught electrode minus RT by NF ln 1 by molar concentration of Mn plus alone. So, you can see that the electrode potential depends only on the molar concentration of the electrolyte. Metal is not involved because it is in the 100% pure form. So, the electrode potential, when this concentration changes, automatically the electrode potential also changes. Okay. Now, I am going to convert this into the logarithm to the base 10. We have to multiply the term with 2.303. Here again, now the expression takes the form E of electrode is equal to E naught of electrode minus 2.303 RT by NF log 1 by the molar concentration of Mn plus ions. Now, we all know that R is a universal gas constant and its value is equal to 8.314 joules per Kelvin per mole. And Faraday, as I have told earlier, is equal to 96,500 coulombs. Now, one more factor we were saying was temperature. Now, if the temperature is fixed to 298 Kelvin, that is 25 degrees Celsius. If I fix it, now all these except N, because N depends upon what type of electrode reaction is going on, and therefore, excluding N, the other factors become a constant. Substitute them, you get the expression modified as E of electrode is equal to E naught of electrode minus 0.0591 by N log 1 by molar concentration of Mn plus. So, this will be the mostly used equation, because most of the reactions or the electrode cell setup will be at the room temperature, and we assume the temperature to be 298 Kelvin. So, for the sake of problems as well as considering the Nernst equation, we will be mostly considering this one. Okay. Now, I am going to do this is we were doing it only for a metal and metal ion electrode. Now, we are going to do a general form for Nernst equation, which is applicable to all electrodes. So, I am going to represent the electrode reaction. If you remember, I have always told that we have to identify the oxidized state, and in terms of you take the oxidized state, add the number of electrons required, and you get the reduced form. You have to write it in such a way. So, in a general form, oxidized state plus Ne electron gives the reduced state of that particular substance. Now, here E of electrode is equal to E naught of electrode minus 2.303 RT by NF log molar concentration of the reduced state divided by molar concentration of the oxidized state. Now, here if you have noted, it is just like when you are calculating the equilibrium constant, where we take the product of concentration of the products divided by product of concentration of the reactants. Just like that, in the case of this electrode reaction, here these are the reactants and these are the products. Of course, we do not include Ne, that is the number of electrons involved, that is taken as N here. So, here we have the molar concentration of the reduced state divided by molar concentration of the oxidized state. So, this is the general form where we can apply it to any system. For example, if I am taking an electrode reaction, that is a redox electrode, we have been talking it in the last class, that is platinum dipped in a solution of Fe2 plus aqueous, comma Fe3 plus aqueous. Now, the electrode reaction will be identify the oxidized state, that is Fe3 plus, takes up 1 electron to give Fe2 plus. So, this is the electrode reaction where Fe3 plus and Fe2 plus are in aqueous solutions. Now, in this case when we write the electrode reaction, we have seen that on both sides we have the aqueous media ions, and in both cases you will have to consider the concentrations, and therefore, the Nernst equation in such case will be E of electrode will be equal to E naught of electrode minus 2.303 R T by N F. N is equal to 1. So, I can put it as just F log. Here the products are Fe2 plus ion. So, you have to take the molar concentration of Fe2 plus divided by molar concentration of Fe3 plus. So, in this case, in the first case when I took metal, you got only one of the metal ions at the denominator. Here both the products as well as the reactants you have ions, and therefore, both are involved in the Nernst equation. Now, let us see how to solve Nernst equation for this example. Here a copper rod is placed in a solution whose concentration is 5 into 10 to the power minus 3 molar, temperature is 298 Kelvin. We are asked to calculate the potential of the electrode at 298 Kelvin. The E naught value for copper is given. It is clear that is an application of Nernst equation for the electrode. Now, here you can see that all the values are given, and this is a clear example for Nernst equation for an electrode. So, I will put the Nernst equation as E of copper 2 plus copper is equal to E naught of copper 2 plus copper minus the temperature is given as 298. So, we can give the value as 0.0591 divided by N log concentration of copper, that is the reduced state, divided by concentration of copper 2 plus. You can find out the value of N very easily, because we know that the ion involved is Cu2 plus, and that has to be converted into copper, which requires 2 electrons, or in the other way you can do it, you write the electron reaction and find the value of N. So, here we get the value of N as N is equal to 2. Okay. Now, substituting these values and the concentration of copper, we get E0 of copper, it is given as 0.34 volts minus 0.0591 divided by 2 log concentration of copper being pure, that is equal to 1. So, 1 divided by concentration of copper ions, that is equal to 5 into 10 to the power minus 3 molar, and solving for that you will get the answer as 0.27201 volts. Now, in a similar way we are going to find out the EMF of a cell. So far we have been dealing with electrodes, now we are going for the cell. For a cell, as we have seen earlier, E of cell is equal to E of cathode minus E of anode. For a standard cell, as we all know, when the conditions are mentioned, E naught cell is equal to E naught of cathode minus E naught of anode. Next, we are going to apply the Nernst equation for EMF of the cell. Now, consider the cell reaction. So, this is the cell reaction. A moles of A and B moles of B, giving C moles of C and D moles of D. So, just an imaginary one. And I have told you in the Nernst equation, we have been applying here, that is after log, you will be giving just like the equilibrium constant we are taking, just like that we will be taking the molar concentration of the products by molar concentration of the reactants. So, here for instead of electrode we are going to take E of cell, then here instead of electrode again that will be E naught of cell minus 2.303 RT by NF log, these are the products. So, C concentration of C, that is the molar concentration, you have C moles, small c moles of C, and therefore, that should be raised to the power of C, and D you are having D moles, small d moles, and therefore, molar concentration of D raised to D divided by molar concentration of A raised to A and molar concentration of B raised to B. Here this is the standard electrode potential of the cell, which we can calculate. N is the number of electrons in the cell reaction. Cell reaction. Okay. And these are the molar concentrations raised to the power of the number of moles. Okay. Again, we can modify this as E naught of cell minus 2.303 is a constant, R is gas constant, T if it is 298 Kelvin, and Faraday is also constant. So, substituting all that I get 0.0591 divided by N log molar concentration of C raised to C, molar concentration of D raised to D, whole divided by molar concentration of A raised to A to molar concentration of B raised to B. So, you write the cell reaction and then you can write down the Nernst equation for any cell reaction. Okay. Now, we will go for a problem. Set up a standard cell in which the following reaction occurs. So, the cell reaction is given and you are asked to set up the cell. In this case, first thing what we have to do is we have to identify which of this undergoes oxidation and which undergoes reduction. See, copper has been changed to copper 2 plus ions and chlorine has been changed to chloride ions. In the first case, that is copper changing to copper 2 plus ions means it is losing electrons, and therefore, this is the oxidation part. Chlorine acquiring electrons means it is undergoing reduction, and oxidation is for anode. So, this will be the copper will be the anode and the chlorine part will be, there is a gas electrode, that will be the cathode. Now, we can write a cell. First, we have to put the anode, that is copper, in contact with copper ions, copper solid in contact with, better I am going to put a salt bridge instead of a porous diaphragm. Then I have to put the electrolyte solution of the cathode, that is chloride ions, aqueous, chlorine gas. Now, it is not complete because this is a gas electrode, you have to put platinum, otherwise the electrode will not be complete. So, this is how we will set up a cell from the cell reaction. So, you just find out the anode and the cathode, identify them and write first the anode and then the cathode, and remember, if you are having any non-conducting anode or a cathode, mind you have to insert platinum electrode. So, next is another problem. Calculate the EMF of the cell where the copper ion with a concentration 0.25 molar in silver with a concentration 0.6 molar at 298 Kelvin, given E0 of copper 2 plus copper is equal to 0.34 and E0 of silver, ion silver is equal to 0.80 volts. This is again application of Nernst equation, but the thing is we have to find out the cell reaction, only then you can find out the number of electrons involved. So, first we have to find out how much is the value for N. So, here copper is undergoing. So, I will put first the anode part undergoes, copper undergoes oxidation. So, copper gives copper 2 plus 2 electrons. So, this will be the anode. Now, cathode will be silver. Now, how did I identify that? If you remember, just checking the values of reduction potentials. Silver has got more reduction potential and therefore, silver will be the cathode. Now, in this case, one more thing to be considered. Here I am having silver ions, and that silver ions require only one electron to get reduced to silver metal, but since anode is supplying 2 electrons, that has to be consumed by the cathode. So, in this case 2 silver ions will take up these 2 electrons, because copper is pumping 2 electrons per copper atom. So, that will be taken up by 2 silver atoms, silver ions getting converted into 2 silver metal. And the overall cell reaction, as you can see, that is copper solid and 2 silver plus ions in the aqueous medium will give you copper going into aqueous medium and you get silver solid. This is a cell reaction, and from here we get N is equal to 2. Now, since the cell reaction is known, you can write down the Nernst equation. E of cell is equal to E naught of cell minus temperature is 0.298. So, 0.0591 by N. N will be 2 in this case, log. When I take the products, I will take into consideration only the ions. So, here I will have copper ions, and in this case we will have silver ions, but the molar concentration is 2, you have to keep in mind that too. So, log of molar concentration of products is copper 2 plus divided by molar concentration of silver plus raised to the power 2, that is the number of moles of silver. Now, substitute the values, that is E0 for cell. E0 cell has to be calculated. E0 cell will calculate from these values. E0 of cathode minus E0 of anode. The values, cathode is 0.80 minus 0.34. Okay. So, I will substitute that here, 0.80 and 34. In minus 0.591 divided by 2 log concentration of copper 2 plus, which is given as 0.25, and that of silver is 0.6, therefore, there is 0.6 whole square. Solve for it and you will get the answer as 0.4647 volts. So, in this class we have been dealing with the effect of concentration on the electrode potential as well as cell potential. Whenever the electrode potential changes, you can find that there is a change in the concentration of the electrode potential, and the dependence of the concentration on electrode potential is shown by a very good important relation known as Nernst equation, and it is given for both electrode as well as the cell. Thank you.